Hello students, welcome back. Previously we went through what it means by a definite integral and we went through a couple of estimation problems. Now let's do precise computation problem, and that's done by the fundamental theorem of calculus. Let's begin with a continuous function, a continuous real function defined on a closed and bounded interval a to b. Then there's an antiderivative function which is continuous on the same closed interval, and it's an antiderivative, so the derivative is the original function. And finally, the definite integral is the net change. Especially this formula here is used to calculate the definite integral precisely using the antiderivative. Want to see an example? Well, let's begin with this example. By the way, this is very, very famous example. It goes way, way back. Oops. Okay, all right. So, this is capital F of B minus capital F of A. Here, B is 1 and A is -1. So we can calculate like this, if we know what capital F is. So what is this capital F? The derivative is the original integrand. In other words, f of x is the antiderivative function. Can you calculate this? Well, that's a piece of cake. Antiderivative of 1 is just x. Antiderivative of x squared, 1/3 x cubed, and then plus c follows. Is everybody with me here? And use this, plug in x equals 1 and plug in x equal to -1, subtract one from the other, then you're going to get the answer. Make sense? It'll turn out, however, that this plus c will not be that necessary in this case, or any case actually. Let's see, what do I mean by that? I have to plug in x equals to 1. X equals to 1. I have to plug in x equals to -1. Plug in x equals to -1, all right? I did it. And then, please note that this plus c and that plus c would just cancel each other out. No matter what plus c I get, always they're going to cancel each other out, because plus c here minus plus c there, they always go out. And what do you have left? 1 minus 1/3, so that's 2/3, minus negative of that, so it's negative plus. You're going to end up with this computation if you do it right. So this kind of computation is through the fundamental theorem of calculus. The fundamental theorem of calculus has actually 3 parts. Number 1, the definite integral exists. Number 2, the antiderivative function exists. And number 3, the definite integral can be calculated as a net change like this. But this is 1000 level course, so we don't really do anything about they exist something part. We just use this as a formula. let's see, what did I do in this answer key I wrote here? Oh, by the way, that's a picture. And this is a very, very famous picture. And this problem is very, very famous problem, very old. Originally, it was done by Archimedes. And that was, what, 6th century BC, way before the invention of calculus. And he didn't use fundamental theorem of calculus, of course. He did it in completely different method, like this. First, do a triangle like this, and then find out the area of the triangle. Next, get a function value at 1/2, and then get area of this triangle, and that triangle, of course. Add them up. And then next, get the function values at 1/4 and 3/4, and get the areas of this triangle and that triangle. And then add them up, add them up, add them up. And eventually he noticed that the sum of everything approached 4/3. The same 4/3 we calculated before. And that was part of this formula, by the way. And he needed this 4/3, and yes, it turned out it has something to do with this, so we ended up with 4/3 here as precise computation. And that's how he got the volume formula for the ball. 6th century BC by Archimedes. And he was so proud of this formula that he wanted this as an epitaph of his grave, but it didn't turn out that way because he ended up getting killed during the Punic War. Anyway, this was very, very famous example problem, and we went through the solution using the fundamental theorem like this. But then again, let's do this again using an alternative approach. The same idea, same fundamental theorem, but a little bit different approach, a little bit different notation rather, a little bit simplified version. Instead of utilizing this capital F and doing all these over again, we just use shorthand, find out the antiderivative function, this f of x function like this, and then put this bracket, and then from a to b. That's a shorthand of putting capital F of b minus capital F of a, and subtract one from the other. And then, of course, in the end, we end up with the same result as before. Let's see. Do we have enough time for other problems? Okay, here's another problem. Let's go ahead and do that. How about the next problem here? This one here requires some computation before applying any of those antiderivative formula because we are product of two functions. And if we have addition, then okay, we can separate the integral, but product, we can't. So we need to FOIL it out first. So break it off. First, 1 times 2. Outside, 1 times t squared. Inside, negative t times 2. And then last, t to the 3rd power. Did I break up correctly? Okay, that was the first step. And now let's go ahead with antiderivative computation. 2 becomes 2t, so far so good. Antiderivative of t squared, 1/3 t to the 3rd power. And then t squared, and finally 1/4 t to the 4th power. Is everything okay? And then, here's a reminder, we just did the antiderivative computation. We have yet to apply the fundamental theorem. So I'm going to plug in t equals to 0 and t equals to 1 and subtract one from the other. And then let's go ahead and do that. Plug in t equals to 1. Oh, that's easy. T is 1, then 1 to anything is 1. So 2 plus 1/3 minus 1 minus 1/4. That's what we get. And plug in t equals to 0. Oh, that's even easier. Everything is 0. So if you calculate everything and punch this into calculator, let's see what I get. 13/12. Okay, that's the answer. That's how you do this kind of computation. Let's see. This final answer here is not that important for me. This one is important. And then punch in the calculator, you're going to get that. So final line is not that important. First line is important. Here we got a bunch of power functions, and we are ready for antidifferentiation. And this line, of course, is important. That's the antiderivative. So indefinite interval computation, that's important. And this line, here we use the fundamental theorem of calculus. So of course that's important as well. These three are essential lines. For the justification, I need these three. And the final answer here is not that important because once you have this green, punch in the calculator, you're going to get this. So that's how you write your solution, and that's how you justify. Remember, which step is important, which step is not important, you can skip. You have to understand those. If you just don't skip anything and then just write everything, that's going to be the safest. But sometimes you do want to skip, but yeah, here's what I did in my answer key. Let's see, do we have enough time for the next problem here? Well, stop the playback and then go ahead on your own. And I'll check on you a little bit later. Well, did everybody complete the problem? Okay, all right. Here's the solution. First, separate the numerator, of course. If you have denominator and then something added on the numerator, think about this as a first step. Separate the numerator and then simplify term by term, which you did here. And what do you get? We have a bunch of power functions. You're finally ready for antidifferentiation. Next, apply the antiderivative rule. This is the indefinite integral. And then apply the fundamental theorem. Plug in the top, plug in the bottom, subtract one from the other. And then punch in the calculator, we get these, but these two are not that essential. So if you miss these two, no big deal. As far as I'm grading, you can stop here because that's a numerical value, and afterwards that's a computation, just numerical calculation, punching the calculator, no big deal. But these three lines are essential. Ready for the antiderivative, the antiderivative computation, and the fundamental theorem computation. How about the next problem here? Again, stop the playback and go through it. All done? Okay, all right. What did I do here? Oh boy, this is terrible. Okay, what did I do here? First, separate the numerator. Okay. As a result, I got exponential and the constant. Ready for the antidifferentiation here? Yes. Exponential and just constant. Now, this is the antidifferentiation or indefinite integral. And then plug in the top, plug in the bottom, subtract one from the other, the fundamental theorem of calculus. And after that, it's just a simplification, and this one is not that important. These three are essential, which I highlighted in different colors. Okay, so much for elementary examples on antidifferentiation and integration. And then fundamental theorem of calculus. Now we're going to discuss another aspect of fundamental theorem of calculus, taking the derivative of integral, but that's going to be the next video. Stay tuned.